Alright, so far this year we've talked about things moving, and we define that as changing position in either the x or the y direction. And the term for that is translation. But obviously that's not the only way that things can move. And so today we're going to make the connection and the jump to the concept of rotation. And we're going to take all the concepts and the quantities that we've learned in translation and convert them to the realm of rotation. So the first thing we learned about in translation was a change in position that we call displacement. And so this is to move again in either the x or the y direction and change position. But if it doesn't change position translationally, it might be rotating. And to define that, we're going to talk about its angular position, represented by the symbol theta, and therefore its angular displacement, delta theta. And of course the rate that something changes its position, we called velocity, displacement over time. And so we'll have a correlating angular velocity, which is change in angular position over time. And we need to talk briefly about, you've noticed I've added the vector notation. These quantities can be scalar quantities or they can be vector quantities, but it's going to be a little different in how we look at the direction than you're used to in translation. Imagine this wheel, and you can see you can pick the valve stem in the left-hand corner of the picture as a point of reference. As it moves from this position, which on a unit circle you might call half pi, pi, to this position, which is half pi, from the point of view of the viewer, we would call that clockwise as it then moves to this position. But you can imagine if you're on the other side of the wheel, then that would look like it was moving in the counter or anti-clockwise direction. And so we picked a convention in order to describe this direction, and it's what we call the right-hand rule. And what you do to do this right-hand rule is you curl your fingers in the direction that the object is spinning, and your thumb then, when pointing straight out, will point in the direction of the velocity. So in this instance, we're going to curl our fingers around over the top of the wheel. That causes our thumb to be pointing in the direction of the axle away from us. And so this angular velocity would have a direction of away from the viewer. Similarly, if you were to reverse the direction, from this standpoint, it would look like the wheel was spinning counter or anti-clockwise. If I curl my right hand fingers tips in that direction, then my thumb will be pointing towards me. And so that would be an example of where the angular velocity was in the direction towards the viewer or out of the board. So that's a little different, like I said, than the direction of translation, and that's completely just a convention that we've chosen to be able to be clear about directions for rotating objects. Alright, so we've got translation, quantities, displacement, and velocity, and their corresponding rotation equivalents, angular displacement, and angular velocity. Let's talk briefly about units. Obviously, displacement we measure in meters and velocity in meters per second. Angular displacement we can use either degrees or radians or even rotations or revolutions. Therefore, angular velocity can be radians per second or degrees per second or even revolutions per minute, RPMs, or any of those types of units. What we're going to use most commonly is radians and radians per second, and you'll see before the end of this video why that's so important. A brief note about that though, students often ask, well, does that mean our calculator needs to be in radian mode versus degree mode? And the answer is no. Even though we're going to be using radians as our units, the mode on your calculator only applies when you're doing trigonometric functions. And so if you're trying to find sine of an angle or such, then it matters whether or not you're talking about degrees or radians. But for these purposes, it won't matter. All right, so then we then learned about acceleration, the rate of change of velocity, and therefore we're going to obviously have an angular acceleration, and we're going to use the symbol alpha for that. And again, it's going to have a similar direction notation by that right-hand rule. All right, so then notice these are some of our kinematics equations for constant acceleration that we've been using all year. And I want you to notice that we basically doubled the number of equations that we have access to now, because everything that happened in translation, we have a corresponding equation in rotation. So displacement equals the initial velocity times time plus 1/2 the acceleration times time squared finds a correlation in angular displacement equals the initial angular velocity times time plus 1/2 the angular acceleration times time squared. And similarly, where velocity is the initial velocity plus the acceleration times time, the angular velocity will be the initial angular velocity plus the angular acceleration times time. So let's see how this applies to an example problem. If we ask the question, how many rotations will a wheel make in 4.2 seconds if it has an angular velocity of 13 radians per second, then we can ask ourselves what information has been given, and then if we have an equation to relate the unknowns to the known, and then we can substitute. And so identifying the given information, we have 13 radians per second is an angular velocity, and 4.2 seconds is a time, and I'm looking for rotations, which is an angular displacement. And so I can use that first kinematics equation, that angular displacement equals the initial angular velocity times time plus 1/2 the angular acceleration times time squared. Well, it's not speeding up or slowing down, and so the angular acceleration is 0, reducing it to 13 radians per second, which is the initial angular velocity times the time of 4.2 seconds, gives me 54.6 radians. And that's a perfectly good answer to what's the angular displacement of this wheel. But notice I asked for how many rotations. And so we need to convert from radians to rotations. And I'm always going to go back to our friend dimensional analysis that you learned in chemistry. I'm going to take the known quantity, 54.6 radians, put it over 1, and then get a conversion factor to go from radians to revolutions. Well, what is that conversion factor? Well, 2 pi radians is equivalent to 1 revolution. So I put those with the associated units, and then I do the math, and I get 8.7 rotations. Just a quick note of warning here. Be careful when dividing by 2 pi. That is dividing by the quantity 2 pi, and so if you plug that in your calculator times 2 pi, or excuse me, divided by 2 pi, your calculator is going to say, okay, let's divide by 2, and then you want to multiply by pi. And so you have a couple of options to get around that. One is you can, of course, do the 2 pi quantity first and then divide by that number. Or you can use your fraction notation on your calculator and make 2 pi the denominator. Or you can use parentheses, divided by parentheses 2 pi, close parentheses. What I typically do, because it's a lot faster than any of those other methods, is I just always divide by everything in the denominator. And so if I'm punching this in my calculator, I do 54.6 divided by 2 divided by pi, to remind my calculator that that means that both the 2 and the pi are in the denominator. So I'm going to divide by both of them. So 8.7 rotations is the answer to that question. All right, so let's look at another one. Let's say, how long will it take a disk to slow from 18 radians per second to 7 radians per second if the angular acceleration is negative 2.9 radians per second squared? Well, again, I'm going to take the same approach. I'm going to ask what given information we have, and if there's an equation that relates the known to the unknown. And of course, I've got 18 radians per second is the initial angular velocity, 7 radians per second is the final angular velocity. The angular acceleration is negative 2.9 radians per second squared, and I'm looking for a time, how long. And so I find that I can plug that into angular velocity equals initial angular velocity plus angular acceleration times time. Do a little algebra to solve for time, and you get final minus initial angular velocity over angular acceleration will give me that time. And then plugging in the quantities, 7 minus 18 over negative 2.9 gives me a time of 3.8 seconds. Now a quick note about this equation. This is one that we noticed on our equation sheet the other day but just kind of ignored. Basically, let's talk about how we derive this. The quantity angular velocity is a rate of change of angular displacement. And so if I think about the special case of making one rotation, the angular displacement for one rotation will be 2 pi radians, and the time that it takes to make one rotation is also known as the period. And so another way to define the angular velocity of an object is 2 pi divided by its period. And then we rearrange for period, and we get 2 pi over angular velocity. And that's the one that you'll notice on your equation sheet between period and the reciprocal of frequency. And of course, then you could notice that frequency then would be omega over 2 pi. All right, and then now let's find some equations to relate translation to rotation. Think for a moment if you were asking what linear distance would an object undergo as it went through a certain angular displacement, how could we relate those? Well, think of what distance would it go in one rotation? Well, in one rotation, the angular displacement would be 2 pi, and to find the linear distance it went would be the circumference, 2 pi r. And so we can translate that to any distance, not just one rotation, and just multiply the angular displacement times the radius. And that will tell us the linear distance that an object covers. Similarly, if we divide both sides of this equation by time, we get velocity equals angular velocity times radius. And so imagine the wheel spinning, or I use the example in class of the merry-go-round. Everyone on the merry-go-round is going to have the same angular velocity. In other words, no matter where you're sitting on the merry-go-round, you're going to make it around the same number of times before the ride ends. But not everyone covers the same linear distance. The people on the outside are going to go in larger circles, and so they're going to cover a larger linear distance than the people on the inside, as indicated by this relationship with radius. Similarly, everybody's going the same angular velocity, but the people sitting on the outside are going to be going faster in terms of the linear speed. And then finally, if we divide both sides by time again, we get the linear acceleration equals the angular acceleration, again, times the radius. And so these equations help us to connect, again, rotational motion to the linear motion that happens at the same time. But and this is where what I said earlier about radians is so important. These equations only work when those angular quantities are measured in radians. And so that's why, even though there's several options for angular units, I'm going to always encourage you to get to radians before using any of your equations. All right, so let's look at one final example then. A wheel of radius 0.4 meters starts at rest and accelerates to 14 radians per second in 4.1 seconds. How many meters did a point on the edge of the wheel travel in a circle during that time? So here again, we got to look at what's given and see if we have an equation that relates the known and the unknown. And I'm going to take two different approaches to this. The first is a little bit faster, but maybe not as intuitive to most students. But I'm going to ask myself, what was the average angular velocity? Well, if it went from 0 to 14 radians per second, so long as there was a constant acceleration, which there is all this year, we only have constant accelerations and therefore constant angular accelerations. Well, as long as it's a constant acceleration, the average is just the midpoint between those two points. So if it went from 0 to 14, then the average was 7 radians per second. And just like the average linear velocity is the distance over the time, the average angular velocity is the angular displacement or distance over time. And so rearranging for angular displacement, I get average angular velocity times time, which again was 7 times the time of 4.1. And then that gives me, it goes 28.7 radians. So if it goes 28.7 radians, all that's left is to find out what linear distance that was. And so I use that last equation we just derived, which is that the linear distance equals the angular displacement times the radius. And that's 28.7 times the 0.4, and that tells me that it goes 11.4 meters. Now let me work at a second way that most students would gravitate towards, and that is to go to that kinematics equation. First, we're going to calculate the angular acceleration, which is the change in angular velocity over time. It went from 0 to 14, so that's a change of 14 divided by 4.1 seconds is 3.4 radians per second squared. It's the angular velocity, the angular acceleration. I plug that in then into delta theta equals the initial angular velocity times time plus 1/2 the angular acceleration times time squared. Gives me 1/2 of 3.4 times 4.1 squared. Again, because it started at rest, and so the initial angular velocity is 0. Well, if you punch that in your calculator, you'll find that that's going to give you the exact same answer, the 28.7 radians. And then again, the final step will just be multiplying by the radius to get the 11.4 meters. So either of these approaches works. One's a little faster, but maybe not as intuitive as the other. So in review, today we learned multiple new equations. We found that all of our constant acceleration kinematics equations have corresponding angular quantities that work just the same way. We found a relationship for period that talks about rotating objects. And then we found 3 equations to help us translate back and forth between translation and rotation. But again, you've got to remember to make sure that your units are in radians whenever using those equations. All right, very good.